One major roadblock in the way of achieving general-purpose robots is task generality of learned representations. In this project, Latent Skill Transfer for Simulated Agents, I investigate how learned high-level skills can be transferred between similar tasks to accelerate learning of new tasks. One existing approach that attempts to do this is model-agnostic meta-learning, or MAML. MAML is a general-purpose approach for fast adaptation of deep neural networks. It attempts to find a parameter assignment in the observed space that is somewhere close to optimal for various environments in the gradient space. The main divergence of our work from this existing body of work is the fact that we attempt to learn these general purpose representations in a latent space as opposed to directly in the observed image space, for example. Thus, the objective is to learn some optimal policy that achieves high reward on the target task given learned information from some previous task. There are a variety of ways to do this, the most naive perhaps, which is directly training whatever model on the pre-trained task and then just carrying that same exact model with no modifications and training on the target task. That gets mediocre results, and we've actually demonstrated that in the upper left corner of the results and analysis section. However, our approach attempts to modify the soft actor critic method, which is already state-of-the-art for most continuous control problems. And what we do is we operate policy learning in the latent space. So we factorize our conventional policy, which goes from the state to action distribution, into a low-level policy that maps from the state to latent distribution. Then we introduce an action generator, which maps from this latent distribution to the action distribution. But then the main contribution is that we actually share this action generator, repurposing it as the decoder of a conditional variational autoencoder. The purpose of this is, one, we can learn a low-dimensional representation that's regularized to be a unit Gaussian prior, and also we can have this decoder begin to re-weight what we think are hopefully going to be more generally positive actions and de-weight actions such as flailing and jerking motions that we don't want to learn for any task. The results of this are shown in the results and analysis section, where we compare our approach to directly using soft actor critic on the target task. Although we don't achieve as high rewards as we would have hoped, we think that a variety of modifications can lead to increased sample efficiency that can make this approach worthwhile, such as introducing a better variational prior that is more expressive, or perhaps using a different, more expressive latent variable model.